Hello, everyone. My name is Xiaofeng Liao. I'm from the Center for Molecular and Biomolecular Informatics, Radboud University Medical Center, the Netherlands. Here I would like to present our work with the title A Fair Data Model for the PRISMA study. PRISMA stands for Personalized Risk-Based Mammal Screening. In the Netherlands, women aged 50 to 75 years are invited to receive breast cancer screening every 2 years. PRISMA study aims to optimize the effectiveness and efficiency of breast cancer screening through personalized screening regimens based on a women's risk of breast cancer. With this slide, I would like to give you some numbers of the data we collected on breast cancer risk factors. As mentioned, the PRISMA study carried on the population-based cohort of women of between 50 to 75 years. We collected 70,000 unprocessed mammograms, and there are altogether 43,000 health questionnaires were completed by the participants. And we also collected 10,500 blood samples. All these data are supposed to be linked to Dutch Cancer Registry. For this work, we mainly focus on the 43,000 health questionnaires. But we find a critical problem when we collecting this data. That is, there is no universally accepted data model for the collection of breast cancer risk factors. This lack of interoperability would impede the clear data representation and the communication globally. And the collected data has potential for validation work in the machine learning application, but this is obviously hindered by lack of interoperability. So with this work, we have two objectives. The first one, a general one, is to reduce ambiguity of data schemes in the domain and increase secondary use of client-reported outcomes through verification. That is, to ensure data are findable, accessible, interoperable, and reusable. The second objective is, more specifically, we'd like to create a fair semantic data model out of the PRISMA questionnaire. Let's first have a brief look of what the questionnaires looks like. As mentioned, we collected 43,000 questionnaires, and each questionnaire has 211 questions. These questions cover a wide range of topics, as illustrated in the word cloud on the right. You can see from this graph some typical questions, for example, participant medical history, smoking habits, family history of cancer, body shape, infant pregnancy, and alcohol use, and about the treatment and the type of cancer, etc. This slide illustrates how the questions are processed in an iterative procedure. The procedure starts from the question. For example, we have a question, have you ever been diagnosed with a form of cancer? For this question, an ID or variable is identified. So in this case, the variable is diagnosed with cancer. The next step in the procedure is to find a code system. In this case, we find the NCIT, National Cancer Institute thesaurus. And then in this code system, we try to find a match for this variable. So this is the code we find for this variable. After processing the first question, the procedure continues on the second question. In this case, the example is, with which type of cancer were you diagnosed? And also an ID or variable was identified for this question, in this case, type of cancer. And also for type of cancer, we tried to find a code system, in this case again NCIT, and we tried to find a map for this type of cancer variable. This procedure continues for all the questions. Here we have the third example, but for time reason, we not go into detail for that one. As maybe mentioned, we have 43,000 questionnaires, and each questionnaire has 211 questions. So this procedure goes through all the questions in all the questionnaires. I'd like to say this is a huge amount of manual work. With this iterative procedure finished on all the questions, we build a linked data representation for all the variables identified from the questions. This slide illustrates how we process the answers provided by the participants, which is similar to the procedure in the previous slide that processed the questions. In response to the questions raised in the previous slide, that which type of cancer a participant was diagnosed, the participant may provide an answer which can be found in the list on the right. For the answer options in the list, again we try to find a code system, and in that system we try to find a map for that options. So in this case, for all these type of cancers, we choose the MAT-DRA code system, and in this system we find all the maps for this type of cancers. After introducing how the iterative procedures was applied on the question and the answers, you may already see we are trying to find an exact match in the existing code system for the variables and the answer options. In this way, we are building up a linked data representation for all these variables and the answer options. As mentioned in the beginning, we find a critical problem for the breast cancer risk factor is that there is a lack of universally accepted semantic data model for this breast cancer risk factor collection. This problem can be easily seen in this bar chart. This bar chart illustrates how many variables are covered in existing code system. For example, the most frequently used code system is the NCIT, but unfortunately, it only covers around 120 variables. Other code system unfortunately only covers very few of the variables. So with this bar chart, I hope you would easily see the problem of lacking of a universally accepted data schema and the necessity that we need to define a universally accepted data schema for the breast cancer risk factor collection and make it fair. After identifying the 188 variables we see in previous slides, we continue to determine common data elements. Altogether, there are 67 data elements were determined out of the 188 variables, and these 60 data elements were grouped into 15 main classes and form this hierarchy. The data elements and the main classes keep a is-A relationship. Let's see some example. Family history of breast cancer is a subclass of family history of cancer. Also, family history of cervical cancer is a subclass of family history of cancer. Also, another subclass is family history of ovarian cancer. Another example is that non-surgical procedure is a subclass of treatment, and chemotherapy is a subclass of non-surgical procedure, and the surgical procedure is a subclass of treatment, and the breast enlargement is a subclass of surgical procedure. Till now, we have identified the common data elements for the breast cancer risk factors and organized them into a hierarchy with is-A relationship between the main class and the subclasses. Further on, I would like to introduce how we use the semantic science integrated ontology on our common data elements. The science ontology is capable of modeling entities, processes, and their qualities or attributes. These three things, entities, process, and qualities attributes, forms the key object of the science ontology, as can be seen in the graph, object, process, and quality or measurement value. On the other side, most of the concepts derived from the questionnaire are measurement of some attributes of the women who participate in the study. We can build a connection between science ontology and our data element, as illustrated by the link. For example, we can connect entity with women and the process with the measurement, with the qualities or attributes with the attributes in our questionnaire. So with this beautiful match between the science ontology key object and our questionnaire data elements, the data elements identified in the PRISMA study can be instantiated according to the core elements in SIO and connected using the established property. With this slide, we would using a concrete example to show how the science ontology can model the question and answers in one single framework. In our case, we could have a participant which can be viewed as an entity. This entity may has a role as a client, and this role can be denoted with an identifier. The identifier could have a specific value, and this role is realized in some process, and this process could have a type of literal, and with the value, a specific value, is our question. For example, have you ever had a surgical procedure for breast cancer? And for this process, it could have an output, which may be some measurement, and this measurement maybe has a value. For example, in this case, maybe a yes or no, and this answers refers to an attribute with the type of Boolean. So you can see that with this psi ontology, with its key components, entity, role, process, our questions and answers can be brought together into one single framework. So we finally come to the conclusions. In summary, 67 common data elements were identified from the questionnaire and grouped into 15 main classes. And the questions and answers were modeled utilizing core elements of the semantic science integrated ontology. And finally, a fair data schema for common risk factors for breast cancer was built. Let's examine from four perspectives. First, find-able. We published this data model on external repository on GitHub. The second principle, accessibility. We choose a license for our model. The third principle, interoperability. Linked data representation for data elements were constructed. And the last one, reusability. We hope that this semantic model can be a potential template for other breast cancer research groups and real-world experience questionnaires. Some future directions. The first one would be model question hierarchy. In a questionnaire, there are some follow-up questions which could be modeled better considering modeling a hierarchy. The second one would be invite use cases that the PRISMA semantic data schema can support. And the last one would be consider the interoperability with other standards, like the electronic health record. Finally, we would like to thank all the collaborators from different affiliations and different projects, including Crossomics, PRISMA Study, European Joint Program for Rare Disease, and the sponsors for this project. And thank you for your time and attention. I would like to take any questions.